Welcome to Design World's How to Calculate series, where you learn how to apply the most important equations for sizing, selecting, and comparing linear motion and motion control products. In this session, sponsored by Dynatect, we'll learn how to calculate the back-driving torque for ball screws and lead screws, and how to determine whether a screw assembly is likely to backdrive in a given application. Ball screws and lead screws are typically used for converting rotary motion to linear motion. But when a load is applied axially to the nut, they do the opposite and convert linear motion to rotary motion, causing the screw to turn. This phenomenon is known as backdriving, and it's typically an undesirable effect of axial loading. Although backdriving can happen regardless of the screw's orientation, it most often occurs in vertical applications, especially if the load is stationary and the holding mechanism, such as a brake or a counterweight, fails. Some drive mechanisms, including belts, rack and pinion drives, and linear motors, aren't typically recommended in vertical applications because if the motor loses power, they allow the load to fall. But ball and lead screw drives are less likely to allow a load to free fall in the event of power loss or failure of the motor. And if the load does begin to drop, if it causes the screw to backdrive, the fall will happen at a somewhat controlled rate, since the force of the falling load has to work against the friction of the screw assembly and the inefficiency inherent in the screw thread. Lead screws are low efficiency drives and therefore typically have very low tendency to backdrive. On the other hand, ball screws are more efficient, making them more likely to backdrive in vertical applications. It's relatively simple to determine if a ball screw or lead screw will backdrive. First, calculate the backdriving torque caused by the load. This is based on the axial load, and don't forget to include the effects of gravity, the lead of the screw, and the efficiency of the screw assembly when operating in reverse. Keep in mind that the screw's reverse efficiency is typically lower than its efficiency in normal operation, so be sure to check the manufacturer's specification for the reverse efficiency. Let's look at an example using a 16 by 10 ball screw assembly with a fixed floating bearing arrangement, a reverse efficiency of 0.8, and an axial load of 100 newtons. The backdriving torque is calculated to be 0.13 newton meters. Now compare this to the sum of friction torques of the screw assembly. These include the friction torque of the nut, seals, and end bearings. These values can usually be found in the screw manufacturer's catalog. For our example, the ball nut has a friction torque of 0.03 newton meters, the end seals have a friction torque of 0.08 newton meters, and the end bearings have a friction torque of 0.15 newton meters. So the total friction torque of the assembly is 0.26 newton meters. In this example, the backdriving torque of 0.13 newton meters is much less than the total friction torque of 0.26 newton meters for the screw assembly. This means that backdriving is unlikely. Even though our calculations indicate that the ball screw is unlikely to backdrive, safety is always the most important consideration in a vertical application. Knowing the probability that a load will cause a screw assembly to backdrive is not a get-out-of-jail-free card to disregard fail-safe mechanisms. Instead, this information should be used as a tool to help you choose the appropriate safety mechanism, such as a supplementary brake or a counterweight, to prevent equipment damage or personal injury. For more information on ball screws, lead screws, and other linear motion topics, visit linearmotiontips.com or designworldonline.com. Thanks for watching.